So, students, good afternoon. Today we'll continue with the previous lecture, whatever we covered, the advanced principle in dynamics. So, in the previous lecture, I said key the Newtonian approach becomes complex when the system is having more degree of freedom system. So, we will be covering in this particular chapter two advanced principles. One is Hamilton principle, another is the Lagrange's equation. Both they depend upon the scalar quantity, that is the energy, potential energy and kinetic energy, or the work done. And in the previous class, I covered how to obtain the potential energy or the mechanical system, the strain energy in a system. So I have took very simple example, but I try to cover basic principles of the strain energy, how the conservative system is there, non-conservative system is there. So we will continue with the same topic, and so today we'll cover. I will start with the generalized coordinate, and then I will take up the Hamilton principle. So let us see the slide. Okay. So I hope you are able to see the slide. Okay. Okay. So generalized coordinates. In the last class, even we discussed the degree of freedom of the dynamic system. Degree of freedom is nothing but the minimum number of coordinates required to define completely the motion of the system. This set of generalized coordinates are actually in any system, like this is a two pendulum system in which the two masses are there, m1 and m2. We can have coordinate of the m1 is x1, y1, and coordinate of m2 is x2, y2. Also, we can have the orientation of the, let us say, this length L1 as theta1, and of the second pendulum, which is connected below that, is theta2. So we have so many coordinates to choose from. But as we know, this particular system is having 2 degree of freedom. So we can able to choose any of these two coordinates. Like we can choose theta1 and theta2 as one set of generalized coordinate, but we can even choose x1 and x2 as another set of generalized coordinate, or x1 and y2 as another set of generalized coordinate. So among these various possible coordinates which we have, we need to choose only 2 coordinates because the degree of freedom is 2. Other coordinates are related with these coordinates. So the set of generalized coordinate is the minimum number of coordinates or parameters. Not necessarily they are always the coordinate of this system that is required to describe the system motion. Okay. So set of generalized coordinate, their number will be equal to degree of freedom of the system, number of degree of freedom system, but we will be having choice which set we need to choose, and the choice of the coordinate will depend upon what the equation of motion we will get. Equation of motion will be having different form if we take a different set of generalized coordinate, but final characteristic of the system will not change. like natural frequency and other things will not change. Only the equation of motion form will change. So the choice of the generalized coordinate should be such that we should get a as simple as equation of motion. As we'll progress in this particular course, we'll see how we can able to choose the generalized coordinate in more effective way. You can choose any one among these, any two, but only thing is the equations may become complex. So especially for, let us say, for this kind of case, theta 1 and theta 2 generally is more convenient in getting the equation of motion. They are simpler in nature, as against if we take x1, x2, or x1, y2, or any other combination. So generally, these generalized coordinates in a particular set, if we take one set, let us say theta 1 and theta 2, they're independent of each other. They're independent of each other, and they're equal to degree of freedom of the system. Generally, we represent the generalized coordinate as, let us say, for n degree of freedom system. If you want to generalize, so q1, q2, dash dash qn. So for n degree of freedom system, we'll be having n number of generalized coordinate. For the present problem, we have 2 degree of freedom, so we have only q1 and q2, which is equal to theta 1 and theta 2. Okay. So because these coordinates theta 1, theta 2, x1, x2, y2, and x2, they are geometrically related. You can able to relate theta 1 with x1 or theta 1 with y1. Similarly, x2, y2 with this one. So once we have the relationship between them, so we can use some kind of coordinate transformation that also we'll study in the next chapter. If we have one set of generalized coordinate in which we have equation of motion, we can, if we want to transform the equation of motion into new set of generalized coordinate, we can able to transform using the standard transformations, which we'll be studying in the next chapter. So it's not key once we obtain the equation of motion in one set of generalized coordinate. If you want to find out equation of motion in another set of generalized coordinate, there's no need to rederive it. Just using transformation, we can able to get the equation of motion in a new generalized coordinate set. As I mentioned, the choice of the generalized coordinate will decide what will be the form of the equation of motion of the system. Okay, so the constraint relation is same as, because these coordinates are related with each other, so they are called constraint relationship. Okay. Yeah. Here one typical example of the coordinate transformation is given. Actually, is not related with the previous pendulum problem, but let us say we have a relationship between the three coordinates x1, x2, x3 is given by this equation. That is a constraint equation. Actually, this particular system, even it is a 3 mass system, is having only 2 degree of freedom, x1 and x2. So this relationship, which is relating the x1, x2, x3, can be written in terms of x3. So x3 will be, just we bring the x1 and x2 in the right side and divide by m3. So we will get a relationship between x1 and x2 with the x3. So this is one of the relations. Other identity is x1 is equal to x1, x2 is equal to x2. So we have these equations. We can able to combine them in a matrix form like this. So if you see x1, x2, x3 on the left side, x1, x2, x3. So sequence of the equation is, this is first, second, and this is the third, x1, x2, x3. So if we multiply this, we will get x1 is equal to x1 from first row, then x2 is equal to x2 from second row, and x3 is equal to this from the third row. So we have assembled these three equations in a matrix form. Now you see that in the last column, all zeros are there. So obviously x3 will get cancelled. So this equation can be reduced to like this. This column, the last column can be eliminated. So once we eliminate this, x3 also can be eliminated. So you can see that we have a relationship between x1, x2, x3 with this matrix and x1 and x2. So this is a transformation equation where this matrix is the transformation matrix, which will transform the x1, x2, x3 coordinate to x1 and x2 because we have the one relationship among them. So that means out of these three, only two are independent. The third can be obtained using this relationship. So we opted for retaining x1 and x2 and eliminating x3. So this transformation matrix can be used. So in the next chapter, we'll explore more on this. This is just a glimpse of that, how the transformation can be done, but more formal treatment and the examples will be giving in the next chapter. So, so first thing before going to the Hamilton principle, we will see the principle of virtual work. And initially we'll start with the static case because it is relatively simpler to understand, and then we'll extend the principle of virtual work for the dynamic case. Here, the principle of virtual work will be used to obtain the equation of motion of the system, dynamic system, multi-degree of freedom system. This particular approach is this very basic approach, and you will see that for more complex system, we have difficulty in the virtual work principle, because we need to obtain virtual work for all the forces which are acting in the system, and the Hamilton principle, which I told, that will be more easier to apply as compared to the virtual work. But this is a very basic approach, so that's why we are studying this. So this principle of virtual work is what? This is a basically statement of equilibrium definition of a mechanical system. So it's a statement of equilibrium definition of a mechanical system. So virtual displacement. Virtual means some kind of fictitious, imaginary displacement. So virtual displacement, let us say delta x1, delta y1, delta z1, like this. So if we are n degree of freedom system, we'll be having various coordinates, generalized coordinates of the system, and the delta is representing that we are giving some kind of some change in the generalized coordinates, small change, and the definition of that is these are arbitrarily small changes in the coordinates of the system from original position. So a system is occupying in a static equilibrium position some position it will occupy. So we will give some small deviations, small arbitrary change in the coordinates, and those changes which will give to the coordinates should satisfy the constraints of the problem or the boundary conditions of the problem. If there is a fixed support in a beam, the fixed support, we know that the displacement should be zero or slope should be zero at the fixed support. So the variation at the fixed support we cannot give because we need to respect the constraints of the problem. But beam, if it is there at any other place, displacement are there, we will give some variations in that. So whatever the variations we are giving, we need to see that this should be compatible with the constraints or the boundary conditions of the problem. Another condition is the virtual displacement does not change with time. They does not change with time. Only the variation is given to the generalized coordinate, not to the time. So let us say a constant equation is having this form, a functional form, which is function of x1, x2 like this, and function of time also is equal to some constant. So this is a constant equation. Here, whatever the variation we are giving will be representing by delta, which is virtual variations. D generally we represent for differentials. Differentials we take up the time also, but virtual variations we are not giving for time. Only we are giving for the generalized coordinate. So this is the main difference between the virtual variation and the differentials. And most of the operations of the differentials are valid for the virtual variations. So that we'll see as we go along. So this is one point to remember. So if we give small this arbitrary variations to all the coordinates, so this function will take this x1 plus delta x1, y1 plus delta y1 like that. So all the coordinates we are giving variation by small amount, and all are arbitrary variations except the t we are keeping as it is. We are not giving any variation to t is equal to c. C is a constant. If we expand this using Taylor series expansion, then we can able to write the function as it is. Then its differentiations with respect to all the coordinates. So you can see that we have x, y, z, three coordinates are there, and if we have n number of masses, so we'll be having these terms n times. So here it has been kept in a summation form. So I is equal to 1 to n is representing that for n masses, this expansion has been done. For that many generalized coordinate, we have done the expansion is equal to c. So now you will see that after Taylor series expansion, this term is actually from this equation is equal to c. So this and c will get cancelled. We will be left with this equal to 0. So that is in the next slide. This is the first derivatives, and the higher derivatives we have ignored. Or we could have taken higher second derivatives and third derivative, that we have ignored. Only we have taken the first derivative in this. So here that approximation is there. So okay. So as I mentioned, these variations which we are giving to each of the coordinates. So this is for the three-dimensional problem in which we can have x, y, z coordinates. We are giving variation to each of them. Okay. So let us say if we take one particle, ith particle among n number of particle in the system, if we take one of the particle I and is acted upon some static or some force, several forces are acting, but the resultant of that is, let us say, Ri. So in a particle I, some forces are acting with their resultant is equal to Ri. Here at present we are considering the static force. So Ri is the static force, the resultant force. But in such system, when it is in equilibrium, because we always talk about system equilibrium, then the resultant force in that particle should be 0. Then only it will be in equilibrium. And for that particular particle, let us say the virtual displacement is Ri. Ri is the polar representation of the position of the particle. It will be having component x, y, z. So this is the variation of the displacement of the rth particle. So what is the virtual work Because of this is the force, resultant force into the virtual displacement. So we are talking about the virtual work. So because we are given this change in the position, which is arbitrary, because resultant force is this, so dot product is giving us the virtual displacement work done. So that is, we call it virtual work. And because this Ri resultant itself is 0, so the product will be 0. So for rth particle, when we are giving a variation delta R, when it is in equilibrium, the virtual work done on that particular particle is 0. Let us see this R resultant force vector. Resultant force vector can have two components. One is external forces F and some kind of constraint forces or reaction forces Fi. So I'm splitting the resultant force into external force plus reaction or the support forces. So if we substitute this in this equation, so and then if we multiply delta R with that, so we will get this equation, because this is the external force multiplied with the variation of that particular particle, and this is the internal or the reaction forces multiplied by the particular particle is equal to 0. Now the constraint forces or the reaction forces, they do not perform work. Like if there is a fixed support, some reactions are coming in the fixed support, but displacement of that particular support will be 0. And as I mentioned, the variation should respect the boundary condition. So once the original displacement is 0, we cannot give variation to that. So in this equation, even the reaction forces are there, but the variation are 0 in the reaction in the constraint forces. So this term will be 0 because this variation is 0. So that is given by this. So here Fi is not 0, but delta Ri is 0 because we need to respect the constraint forces where the displacement will be 0. So virtual displacement will be 0 here. So that means if this is 0, this equation will give only this Fi dot delta Ri. And in the XYZ coordinate, we can able to expand this like this. So this is for one particle. Among n particle, this is the equation for one particle. If we have n such particle, the work done, the virtual work done must be 0 for individual particle. So if we sum up all the virtual work, then that also should be 0. So this is the virtual work for all the particle, or because every particle is in equilibrium, so virtual work from all the individual particles is 0. So if we sum them up for all the particles, virtual work family takes, so we are substituting the W delta Wi here, okay, which we think obtain here. This one we are substituting here, this one, and again expanded the Ri into the external force and the internal or reaction force, and that is equal to 0. And because here the variation in the reaction forces or the constraint forces are 0, so we are left with this with a summation sign. So equation is similar to, but now this is for all the particle in the system, and this is the expression for the virtual work principle. So this will be used to obtain the static equilibrium condition for a n particle system. So this is the expression for the virtual work principle. So what is the statement of the virtual work principle? If a system of forces are in equilibrium, the work done by the externally applied forces due to virtual displacement comply with the constraint of the system is 0. So here is the external force, this is the virtual work we are giving. We are complying with the constraints. That means we are keeping this 0. So whatever the virtual work is there because of this will be 0. Now uh, we know the potential energy is associated uh, potential energy. So if we are giving the virtual displacement to the system, so potential energy also will be changing. So this is the variation of the potential energy due to variation in the uh, virtual displacement we are giving into the system. So potential energy variation can be, because this is a similar to the total derivative, we can write this expression for the variation also. So this is the variation of del v by del x, variation of x, similarly variation of y, variation of z. But we know that in the conservative force field, uh, because when we are giving virtual displacement to the system, we are not changing the system uh, energy. Total energy remains conserved. And for conservative force field, we know that the virtual work done is equal to negative of the change in the or variation in the potential energy. So now this equation and the previous statement will combine. So virtual work we define as force into dr, which is the yeah, and then this is the variation, and this is equal to the potential energy. It is coming from the potential energy. Now, and we know that the virtual work done is equal to 0. So this should be equal to 0. So basically, we have combined the previous expression with the new expression of the potential energy, which we related with the virtual work. But we know the virtual work itself is 0, so we are equating it to 0. Now, in this expression, delta x, variation of x, variation of y, variation of z, all are independent and arbitrary. These delta x, delta y, delta z, we can able to choose arbitrary, also independent of each other. So if that is the case, that means this equation will satisfy only when individually these components are equal to 0. This one. So, and that we know there is mathematically this is the condition for extreme value of V, potential energy. Or extreme value means maybe it can be minimum or maximum or the stationary value or the so-called the local extremes. But when the potential energy, if you're getting minimum, that is the stable equilibrium. This stationary value may not be stable equilibrium. Okay, so I'll take some questions. Then I will go for the dynamic case. Just wait. So you raise your hand. If you have any question, please raise your hand. Okay, so till now there is no question. So I will proceed. So the virtual work principle I described for static case. Now we'll extend that for dynamic case, because in this particular case, in this particular study, we need to do the dynamic analysis. So we know that using Newton's second law, we can able to relate the forces acting on the system, either this external force or internal force, is equal to rate of change in the linear momentum, time rate of change of linear momentum. If we bring this on the left side, then we can think of that a system is in equilibrium, or it is in the dynamic equilibrium under external force, reaction force, and a fictitious inertia force. So system is in equilibrium as we have in the static case, where the motion is not taking place. But once we have the forces in time dependent, motion will also take place. So inertia force will come. So if we bring the inertia force in the left side, then we can say that the system is in equilibrium, dynamic equilibrium, uh, under the external force or internal force and the inertia force. And this is nothing but the D'Alembert's principle, which is derived from the Newton's law. This is for the linear momentum, but same is applicable for the angular momentum also. So how we can able to use this to extend the virtual work principle? So principle of virtual work can be extended as, so this was the external force. So this was the for one particular particle. So now you can see the additional term is coming because of the inertia force. This one, the rest of the thing is as it is. This is zero because the corresponding virtual displacements are zero, which is the constraint of support forces. And for n number of particles, we can sum this up. So if we sum them up, and if you want to write in the x, y, z component, we can write like this, x, y, z component. So now you can see that this is the external force, this is the inertia force, mass into acceleration in the x direction of ith particle, and we are adding all such particle. Similarly in the y direction, z direction. But finally, this virtual work will be zero, as right hand side is zero. Okay, so this is the virtual work principle. It's a simple extension in the dynamic case. I will take up a few examples, and then things will be more clear, because whatever I explain is very general description or more general formulation of the virtual work principle. So I'll take up a couple of examples. Uh, so first I will take the static case so that the concept is more clear, and then maybe in the next class we will take another example for the dynamic case. So you can see there is this a bar is there, which is connected by rollers at the ends, and this bar is also attached with a spring. These rollers can roll over this passage. So you can see the left end of the bar can have horizontal motion, and the right hand of the bar is having vertical motion. So that means this is the unstretched position of the spring, because the gravity is acting. So if we leave this system, it will occupy some equilibrium position. Because of gravity, it will pull toward downward direction. So the spring will get stretched like this. So dotted one is the original position, and the solid one, you can see this roller reached here, and this roller reached here because of the gravity. So this bar will be having some theta angle due to the weight and the spring force. Now we need to find out what should be this angle given mg, stiffness of the spring, and the length of the bar. What will be this angle theta at which this particular system will be in equilibrium, in static equilibrium? And we know that it will be having a unique one position. So that particular position theta we want to know. This particular system is actually single degree of freedom system. See, this a bar is there, and bar is moving in a plane. So a bar can have 3 degree of freedom in a plane if it is moving in a plane. So what are the 3 degree of freedom? It can have x and y displacement and the orientation. So 3 degree of freedom is there, but in this particular problem, the two constraints are there. The left hand is constrained to move in the horizontal direction, right, and of the bar is constrained to move in a vertical direction. So out of 3 degree of freedom, 2 constraints, so only 1 degree of freedom is left out. So actually, only 1 degree of freedom or one generalized coordinate is enough to define the position of this particular bar. So you can see that we can have a choice of the displacement of the left hand x, or the right hand this is a y displacement, or theta. So among x, y, or theta, we can choose any generalized coordinate 1, because in this particular case degree of freedom is 1, so generalized coordinate also will be 1. So finally we need to write the expression in terms of one of these coordinates. Okay, so I hope this is clear. And here I have taken the axis, let us say this is the origin and y is in the upward direction, having unit vector j, and the horizontal direction is right side x, and unit vector is I. So you can see that x is having positive displacement direction, because from position 4 to 1, x is having direction or displacement in the positive direction. But y we have taken upward, so this particular displacement is negative because it's going in the opposite to the y-axis. So let us see the same figure here, and now we'll see what are the forces acting on this particular bar. So one force is here which is acting, which is mg, downward direction, which is negative direction as compared to what we have chosen, the y direction, upward. So this particular force F2 is minus, because it's opposite to the y, minus mg j. J is the unit vector in the y direction. So this is the force on the bar on the right side. In the left side, because the spring got extended by x distance, so, and the force direction will be opposite to the displacement, because displacement is taking place this direction. The restraining force of the spring will be there in the 1 to 4 direction, opposite to the x. So that's why minus kx. K is the stiffness of the spring, x. So is the kx is the spring force, and I is the vector in the x direction. So these are the two forces acting in the this particular system. The position of the end 1 and 2 can be given like this. First position is R1 is, because this is moving in the horizontal direction only, so only the x component is there, xi. This end is moving in the negative y direction and is having no component in the x direction, so negative yj, because and 1 and 2 both are having single direction motion, so other components are not coming, only the x component and y components are coming in the left hand and the second hand. Now if we take the variation of this, the variation of the generalized coordinate will be delta x. If we take the variation of R2, then the variation of this will be delta y. Variation of the vector will not be there, unit vector will not be there, only of the y will be there. So now we have the virtual displacement of the in the left hand, virtual displacement in the right hand, and these are the forces. So we need to find out what is the virtual work. So that will be nothing but this force and this virtual work multiplied by this force and virtual displacement this. So these are the displacement, actual x and y displacement. Around that we are giving a small variation of the delta r. So small variation we are giving here. Small variation we are giving here, and yes, we are obtaining the virtual work because of those variations. These variations are very small, and they are satisfying the constraint that this roller cannot go in the upward direction. So we need to give the variation only in the x direction, this end. Similarly, at this end, variation will be giving only in the y direction because this cannot go in the x direction. So this is the constraint we need to satisfy while giving the variations. Okay, so in the second end, we cannot give variation in the y direction. So here, variation in the x direction. So you can see only the y direction which is given. Now we are applying the virtual principle here. So force in dot product of the variation of the displacement. So we have two forces. One is the elastic force, or this particular force, and variation is delta x. Similarly, here we have mg force, and variation is delta y. So, this is the total virtual work due to the forces acting in the system, and that should be equal to 0 according to the principle of virtual work. And now what is happening, as I mentioned, we have only 1 degree of freedom system. This particular system is single degree of freedom system. So we need to either replace delta y with the delta x, or if we can replace delta x and delta y both to delta theta, that will be giving us the condition where this particular bar will be in equilibrium. So as I mentioned, delta theta, if we take, it will be more convenient. So now I'm relating the x and y with theta with geometry, and then we find out the variation of the theta. So now you can see x is nothing but total length minus L cos theta. So x is nothing but total length minus L cos theta, L cos theta. Okay. Similarly, y is nothing but L sin theta, L sin theta. So we have geometrical relationship between the these coordinates. Now, if we take the variation of x in this variation of x, as I mentioned, variation operator is similar to differential operator in most of the operations. So variation of the constant quantity will be 0 minus L, then cos theta variation will be minus sin theta. So plus sin, it will become plus sin theta, and variation of theta. So as I'm again repeating, the variation operator delta when we are taking is same as the differential operator. And if we take this simple differentiation kind of thing will be there. Only thing is we need to use the delta theta. Similarly here, if we take variation L, this will become cos theta, delta theta. So delta x, delta y, which we obtain, we can substitute in this equation. If we substitute, so and x also we need to substitute in terms of theta. So minus kx L 1 minus cos theta, this is the x, and this is nothing but the variation of the delta x, this one. Similarly, mg delta y is this L cos theta delta theta. Now you can see that delta theta is common, so we can take out that, and the rest of the terms will be within bracket. Now this variation, because we are giving arbitrary, and we can take that as 0 also. So, or we can have any value. So if we can, any value is there, then obviously to satisfy this equation, the bracket term should be equal to 0, because this we can have non-negative value, because this we are choosing arbitrary. So if we equate the terms within the bracket equal to 0, so this is the condition of equilibrium from which we need to obtain the theta. So if we want to rearrange this equation, that will become like this. So this equation, you can see the theta is there, mg k l. So if we know mg k l, we can able to get what is the position of theta at which this particular bar will be in equilibrium under static condition. So, and there is a constraint here. This is a transcendental equation. So you'll see that there will be infinite solutions, but we need to find out which is the feasible solution among those. So feasible solution, you can see that the theta can take maximum 90 degree because of the constraint. It cannot go beyond that. So we need to choose the solution between 0 to 90, and that will be a feasible solution. This numerically can be tried out for a given parameter using any MATLAB or Scilab software. You can able to find out the position of the theta, and that can be checked. So this is one of the problem. I'll take up another problem. Yeah. So in this example, there are two pendulum. One is this, and another is connected below that. So there are two masses, M1 and M2, and a force P is applied here. So we need to find out when we are applying this force P. So this is also for static case. When force P is applied, what is the orientation of this will take place? The length of the two rods are L1, L, but masses are M1 and M2. So we need to find out what is the equilibrium position of this. So most convenient generalized coordinate will be theta1 and theta2. Here also we could have chosen x1, x2, x2, y2, but that will make the equation more complex. In this particular case, theta1 and theta2, we are choosing the generalized coordinate. And here, because there is a 2 degree of freedom, we will be having choice of giving variation to delta theta1 and theta2 both. So, and these variations will be giving one by one to the system, because we have two unknowns. So two equations we should get to find the equilibrium position of this. We'll take up some questions if you have. Otherwise, I'll take this example in the next class. I'm not able to complete this in this class. So I'll take up some questions if you have. Then, whatever I explained in the first example, if you have any questions, please raise your hand. Okay. So Shekhar.
Hello, sir. Sir, in the first example, sir, you told that degree of freedom will be equal to 3n minus c, sir. Sir, but here the number of particles 3n minus c, sir. But here the number of particles will be 2, sir, because there are two masses. So
two mass. Actually, bar, you know, no bar, rigid bar.
Yes,
okay,
yes,
bar. You can consider maybe n masses, but they don't have the relative motion between them.
Yes, sir.
M1, M2, their length is fixed L. They don't have the relative motion between them. That's why this bar will be having 3 degree of freedom.
Yes, bar will have 3 degrees.
3 degree. Okay. So these masses are attached to the bar ends at the ends. Okay. And the
Yes, sir.
ends, the relative displacement between them are not there because length is fixed.
Yes,
So
sir.
M1 and M2, they don't have the uh, relative motion, relative change in the length. So that,
Yes.
okay. So we are considering that as a bar itself.
Okay, sir.
Okay.
Okay,
Yeah.
sir.
So bar is having 3 degree of freedom system because one end is constrained to move in horizontal direction, another in the vertical direction. So we have two constraints.
Yes, sir.
So 3 minus 2 is equal to 1.
Okay, sir.
Okay.
Okay, sir.
Any other question? Okay. Because this was a new concept, so I'm going slow in this. I'll take up in the next class. Yeah, I think Swabhima.
Yes, sir.
Yeah.
Sir, in the
Yeah.
first problem,
Yeah.
so why aren't we taking the virtual work due to inertia force? Like we're supposed to apply the D'Alembert's principle, and there should be inertia force as well. So why haven't we taken the virtual work due to inertia force?
Uh, that particular problem is static case. We are finding the static equilibrium. So we are
Okay,
assuming
okay.
that we are leaving it to leaving the object, and we want to see where finally it will be in rest. Okay, in the
So
subsequent, yeah,
when we leave the object
yeah,
at any instant,
yeah.
it should have some acceleration, no? Then it will
So
have some
yeah,
inertia.
but we are assuming we are taking okay, whatever the motion finally, uh, what is the equilibrium position? So we'll take the inertia when we'll take the dynamic force. Okay, so in the
Okay, sir.
next to next example, we'll include that. But this is just to illustrate the procedure because in the static case, the procedure is more simpler to understand. When the inertia force and other dynamic forces are there, then the equations you'll see it will be very big. So there, the difficulty in the concept will be uh, more difficult to understand. Okay, so actually this is just to illustrate the method. I've given this particular example. Okay, so in fact,
Okay,
this
sir.
is
Thank you, sir.
this is a part of this. I think applied mechanics course. So statics. This is statics. Okay. Any other question? Okay, I think. Hope. Yeah. Bharat.
Yes, sir. I have a doubt regarding the assignment. We are few are getting like different plots of the final answer, sir.
Uh, uh, all we should be getting the same, huh? But
Maybe because of some errors we are doing, but few are like
yeah.
for example, 10 guys are getting some similar plot and another 10 guys are getting similar plot.
Yeah.
Like
So,
what will be the final answer? Like if you have any solution, like we'll try to do it again.
yeah, these are assignment for you to do it. Okay.
Uh,
So don't worry about the final answer. You just see that if you have any doubt, you email me. Okay. If you
okay.
have doubt, okay, I'm getting stuck here. I'm not able to understand. Or if error is there that you need to remove. If there is some error, so if some concept problem is there, you can email me. But if you are making some mistake somewhere, then better rework it, check it once or twice. Then I think you can able to sort out. Okay.
Oh, okay.
Yeah. Yeah. And because this is the first assignment, just to just start so that you are there in the, along with the course. Okay. So if because I've given the to MATLAB and other things also. Okay. So just to learn so that you can okay should learn the because these simple two-line programs are there MATLAB for plotting. It's not very difficult.
Sir, is it that we have to plot our response, what we got after solving the question, or like we can use some ODEs or convolution functions in the MATLAB and we can plot.
ODE I have not explained, but out of your interest, if you want to check with ODE, that is fine.
In the assignment solution, like we can even put some ODE functions or the convolution function in the MATLAB.
That's what I'm saying. So that is not part of the assignment, but if you want to check your result, which you obtain through theoretical expressions, you're welcome to do that.
Okay.
For checking purpose, not this I did, so I will not do analytical thing. Our thing is the analytical main. Focus is on the analytical solution.
Okay.
Okay, but above and over, if you want to do with OD, we are welcome to do, no problem.
Okay.
Rohan.
Sir, since convolutory integral is symmetric about f of t and h of t, so we can use h of t minus tau instead of we can use f of t minus tau instead of h of t minus tau.
Both form you can use. Both form. No, so you need
is
to
it
see.
correct, na sir?
Yeah, because it's symmetric, it has been derived. So any form you can use it, but finally you should see that plot should, the expression should be same or plot should be same, because both are symmetric. We already proved it in the class, no?
Yes, sir.
We already proved it, so you can use any one, whichever is convenient for you.
Okay, sir. Thank you.
Yeah. Sorbiman.
Yes, sir. Sir, like in the integral theorem, if there are, say, I'm integrating in a particular interval where there are two intervals, and in those two intervals there are two different functions, still that symmetry condition can be applied.
See, that is always there, no? Symmetry. What is the problem in that?
Sir, like in if I'm using the symmetry condition and if I'm not
No,
using, I'm using the standard form.
You want to say you want to use one form in one part and another form in other.
No, no, sir. I'm saying that if I'm using f of t, h of t minus tau, and again in another way, I'm doing f of t minus tau into h of tau. If I'm doing that, I'm getting two different results.
Yeah, but
When
you plot it and check whether you're getting the similar plot or not. The expressions may look different. Finally, plot.
yes, sir. Plots are also different. If because those two equations are also differing, means if I plot those, I guess I'll get a different plot.
Then you plot it and check. Maybe I think
Okay.
we are fundamental mistake you are doing somewhere, because they are symmetric. So you can choose any.
So like in
So I don't
symmetric
think
case, we just take t minus tau equals to lambda, and we then differentiate it, and then we put the limits according to it. So if we do that, then we'll get different limits. Like if we integrate in two different functions.
So maybe you share your thing, and then through email you share that what you are doing it. Then I can able to, I think, pinpoint.
Okay. Okay. Sir. Okay.
Any other question? Okay. Rohan? Okay. So I think take up the attendance. So I'm stopping here.